In previous sections, we learned that the argument of a trigonometric identity can be an angle, a real number, or a variable. It is often desired to find the exact value of the sum or difference of the trigonometric arguments. Hello, my name is Tom Atwater, and in this section, we will define and use the sum and difference formulas for the cosine, sine, and tangent trigonometric identities. Let's define the cosine of a sum or difference. Cosine of a minus b is equal to cosine of a times cosine of b plus sine a times sine b. The cosine of a plus b is equal to the cosine of a times the cosine of b minus the sine of a times the sine of b. Let's do this example. Use an identity to find an exact value of cosine of 75 degrees. To find the exact value of cosine of 75 degrees, use the fact that 75 degrees is equal to 30 degrees plus 45 degrees. And then we'll use the formula for the cosine of a plus b. So the cosine of 75 degrees is equal to the cosine of 30 plus 45 degrees. And then the cosine of 30 degrees plus 45 degrees is equal to the cosine of 30 degrees times the cosine of 45 degrees minus the sine of 30 degrees times the sine of 45 degrees. Both of these angles are special angles, and therefore they're ones we've memorized. The cosine of 30 degrees is the square root of 3 over 2. The cosine of 45 degrees is the square root of 2 over 2. Minus the sine of 30 degrees is 1/2, and the sine of 45 degrees is the square root of 2 over 2. So in the first case, we get square root of 3 times square root of 2 is square root of 6 over 4 minus the square root of 2 over 4. That's equal to the square root of 6 minus the square root of 2 over 4. So that then is a method for using the trig identity cosine of the sum to find the cosine of 75 degrees. I want to jump over to the calculator to show you that in fact is equal to each other. So on the calculator, I've already plugged in these expressions, so let's take a look. On the top, I've plugged in the square root of 6 minus the square root of 2, that quantity divided by 4, and the decimal equivalent is 0.25888, etc. Then I plugged in the cosine of 75, and I have the mode in degrees, of course, and that was 0.25888, etc. So, for example, when you are using or finding the cosine of 75 degrees, if you didn't have a calculator handy, you could use the cosine of 30, which you've memorized, plus 45, which you've memorized, degrees. All right, in solving trigonometric equations, it is often useful to reduce a trigonometric sum or difference to a function of a single variable. Here's an example to help us understand this method of reduction. Use identities to write the cosine of pi over 2 minus x as a function of x alone. To do this, then, we would use the cosine of alpha, or a minus b. We have the cosine of pi over 2 minus x. And that's equal to the cosine of pi over 2 times the cosine of x plus the sine of pi over 2 times the sine of x. And now what we can do is simplify this. What is the cosine of pi over 2? Well, cosine is the x value, and the x value of that is 0. So this is really 0 times cosine x. Then we have plus the sine of pi over 2. What is the sine of pi over 2? That's again the y value for pi over 2, which is 1. So that's equal to the sine of x in its entirety. So what we've just shown is that the cosine of pi over 2 minus x equals the sine of x. You may remember that from the cofunction identities that we talked about, and so you may have been able to just do that automatically because of remembering that the cosine of pi over 2 minus x is equal to sine x because of cofunction identities. Now let's look at the definition for the sine and tangent of the sum and difference formulas. The sine of a plus b is equal to the sine a times cosine b plus cosine a times sine b. The sine of a minus b is equal to sine a times cosine b minus cosine a times sine b. Tangent of a plus b is equal to the quotient tangent of a plus tangent of b divided by 1 minus tangent of a times tangent of b. Tangent of a minus b is equal to the quotient tangent of a minus tangent of b divided by 1 plus the tangent of a times the tangent of b. Next, we'll do an example where using these definitions will provide an exact value. Or use the identities to find the exact value of the sine of 13 pi over 12. So, the first thing that you'd want to do here, maybe, is to convert the 13 pi over 12 into degrees. So 13 pi over 12, and we're going to multiply that times 180 over pi. My pi's reduced down. I'm sorry, that's over 12, my fault. And when I multiply all of that out and, of course, divide, we get 195 degrees. Well, how does that help us? Let's think about 195 degrees. We can rewrite that as 150 degrees plus 45 degrees. Again, both of those are special angles, 150 degrees and 45 degrees, so therefore we'll be able to find an exact value without using a calculator. Now we want to use sine of a plus b. In other words, sine of 150 plus 45 degrees. And then use the formula that's the sine of 150 degrees times the cosine of 45 degrees plus we're doing the sine of 45 degrees times the cosine of 150 degrees. Now, we want the sine of 150 degrees. The reference angle for 150 is your 30-degree angle. So essentially, and we know that 150 is in quadrant 2, so sine is positive. So we're looking for the positive sine of 30 degrees, which is 1/2. The cosine of 45 degrees is equal to square root of 2 over 2. Plus, the sine of 45 degrees is the square root of 2 over 2. And then the cosine of 150, we're in quadrant 2, the cosine is negative. So it's negative, essentially the cosine of 30 degrees, which is the square root of 3 over 2. So what we have then is the square root of 2 over 4 minus the square root of 6 over 4. That's equal to square root of 2 minus square root of 6 all over 4. Well, now I would like to give you the opportunity to find the exact value of a trigonometric sum. Use the identities to find the exact value of the tangent of 105. Pause the video while you work on this problem, And when you are finished, restart the video to check your solution. Let's find out how you did on this problem. The first thing to realize is that 105 is the same as 60 plus 45. And then you want to use the tangent of A plus B, where A is 60 and B is 45. So we have the tangent of 60 plus 45. And using your formula, that's equal to tangent of 60 plus tangent of 45 over 1 minus the tangent of 60 times the tangent of 45. And those are all still in degrees. So the tangent of 60, of course, that's a special angle. And so that's equal to, when you go back to your trig functions, either sine over cosine or it's equal to y over x. Either way you do it, it's equal to, the sine value is the square root of 3 over 2 over 1/2 for the cosine value, plus the tangent of 45 is 1. That's all over 1 minus the tangent of 60, which we just got through saying square root of 3 over 2 over 1/2, plus the tangent of 45 is 1. When you simplify all of that, that's going to be equal to -2 minus the square root of 3. And that's the answer that you should have gotten for your example. Now, in this next example, we will find the function values and the quadrant of a sum and difference angle. Suppose that A and B are angles in standard position. Use the given information to find A, the sine of A plus B, B, the tangent of A minus B, C, the quadrant of A plus B, and D, the quadrant of A minus B, given the information that the cosine of A is 3/5, the sine of B is 5/13, and both A and B are in quadrant 1. Notice that each angle is in the first quadrant, and therefore all of the function values are positive. Now we'll use the Pythagorean identity because we know that cosine of A is equal to 3/5. So we can find the sine of A by setting up the fact that sine squared of A is equal to 1 minus cosine squared of A. Well, we know cosine of A is 3/5, so sine squared of A is equal to 1 minus 9/25, because I've squared it already. Therefore, the sine squared of A is going to be equal to 25 over 25 minus 9 over 25. So 25 minus 9 over 25, 16 over 25. And then we take the square root of each side, and we get sine of A is equal to 4/5. Okay, well, you could do a similar example, a similar exercise to find the sine of B. That is, you could use the Pythagorean theorem, go through that exercise, and the sine of, to find the cosine of B. But again, using the Pythagorean theorem, the cosine of B will be 12/13. Okay, now from each of these pieces of information, we can find the tangent of A and the tangent of B. The tangent of A would be the sine of A divided by the cosine of A. So 4/5 divided by 3/5, which means that the tangent of A is 4/3. And then we want to find the tangent of B, which would be equal to the sine of B, 5/13, divided by the cosine of B, which is 12/13. So the tangent of B is 5/12. The reason I'm doing all of these is that I know I'm going to need each one of those individual values when I get to parts A and B. So let's move on to part A, which was to find the sine of A plus B. Now, the sine of A plus B is equal to the sine of A cosine of B plus the cosine of A times the sine of B. So we just need to plug in these values. The sine of A we calculated as 4/5. The cosine of B we calculated as 12/13. Plus, the cosine of A was given to us, 3/5, times the sine of B, which was also given to us as 5/13. Both of the denominators will turn out to be 65. So on the top here we have 48. On the top here we have 15. So 48 and 15 gives me 63/65. And that's the sine of A plus B. Well, what about the tangent of A plus B? Again, I've pre-written out the tangent of A minus B, and that's equal to the tangent of A minus the tangent of B over 1 plus tan A tan B. And again, I did those calculations earlier, so we plugged them in. The tangent of A was equal to 4/3 minus the tangent of B was equal to 5/12. That's all over 1 plus the tangent of A, 4/3, times the tangent of B, 5/12. To simplify this, we need to find the common denominator for both actually the numerator as well as the denominator here. So the common denominator on here is, of course, 12. We have to multiply by 4/4. And that gives me 16/12 minus 5/12 in the numerator. In the denominator, we have to multiply these, but notice that I can reduce this 4 into itself once and into 12 3 times. So this is 5/9. So this becomes 9/9 plus 5/9. That's equal to then, of course, 16 minus 5 for 11/12 over 9 plus the 5 is 14/9. When we're dividing a fraction by a fraction, we take the denominator and we multiply the reciprocal times the numerator. So that's going to give me 11/12 times 9/14. Here, of course, I can reduce these each by 3, so dividing by 3, and I end up with 33/56. And that's my tangent of A minus B. Now, the last parts were to find the quadrant in which A plus B and A minus B are. Now, if we look back to everything we've done here, the tangent of A minus B turned out to be a positive number. And when we calculated the sine of A plus B, it turned out to be a positive number. If we were to go further and calculate the tangent of A plus B, it would have been a positive number. And if we had calculated the sine of A minus B, that would also be a positive number. Well, what that's beginning to tell us then is that the sine and the tangent of both A plus B and A minus B are both positive, which means the cosine of A plus B has to be positive because remember, tangent is sine over cosine. And if tangent and sine are both positive, then the cosine would have to be positive. That's true for the cosine of a minus b as well. It is positive. Well, what that's telling us is that all of the trig function identities for the sum and difference of these angles are all positive. The only quadrant that's true in is quadrant 1. Therefore, a plus b lies in quadrant 1, and a minus b lies in quadrant 1. Great job in today's lesson. Now, in this section, we have examined the sum and difference formulas for the trigonometric functions of sine, cosine, and tangent. They are very important formulas in calculus, so be sure and practice using them by doing the exercises that your teacher assigns, and we'll see you next time.